Welcome back to the continuation of this proving the L1 identity. So we already started the proof by showing you this expression that the mu b minus nu b is equal to the nu b complement minus mu b complement. So this was with this set b equals to those t's in zp such as mu t is bigger than nu t. So let's continue this expression now. So let's continue the proof with this identity that we just proved. So the mu b minus nu b is equal to nu b complement minus mu b complement. And what we have here, we want to now prove that it does actually maximizes the entropy. So sorry, not the total variation distance. So let's take step 2, which is that we claim that the total variation distance is equal to this mu b minus nu b. And if you remember from the previous lecture, you saw that because the definition was like this, that we had this definition of b being all the points such that mu t is bigger than nu t, then we had that the absolute value of mu b minus nu b is equal to mu b minus nu b without the absolute value. So we basically are claiming this, that this is equal to this mu b minus nu b. So this total variation distance. So proof of this. What we have here is the first thing is that how do we prove that something's maximal is equal to this? Well, first of all, lower bound for this, so if we bound it from below, this is by definition this d mu is at least mu b minus nu b, because this is a subset of the zb, so this is equal to that expression. So this is all okay. And now the upper bound is the more important. So then take for that reason we have to take any subset A in ZB. Okay, and what we want is the following: that the total variation this mu A minus nu A is at most this mu b minus nu b. So that's what we want to prove. So if we can prove this for any subset A in ZP, then we are in a very good shape, because now we will see that this is the maximum, of course, is then less than that upper bound. So what we want to prove is basically this kind of an upper bound. So so again, using basically the additivity of both mu and nu, we obtain the following: that if you take the mu a minus nu a, so this is the quantity we want to consider, what we can do here is that, okay, we can split this into the sets over the other points. So we can take mu a intersection with b and then union a and subtract the b out, plus then minus the nu, the same thing here, a intersection b union a removing b. So that kind of like set theoretical idea that you just basically add and subtract here. So you have your set a somewhere here, and then you have your b over here, and then you basically take the intersection, so this is a intersection b, and then you have a slash b. So you get these two subsets that you have here. Oh, sorry. This a intersection b that you have here, and then you have the complement, which is given by the a complement of this. So this one over here, the complement of the b. And now what you can do is that you can see that these two sets, of course, are disjoint. So what you can do here is that you can reorganize them. You get them into some mu a as b, and then here the same you can get nu A intersection B, and then you have the plus nu A slash B. So by using the additivity structure of the measure. And now you can reorganize them a little bit. So what you can do is that you can subtract, you can put them on the different sides. You can take mu A over B minus nu A over B. So this expression is coming here, and then I'll put this into here. You get, this is plus, I think I obtain mu A minus B minus nu A plus B. Just reordering the terms. And now you can use the definition of the probability distribution. You get that this is actually equal to a sum. When you sum over all the elements A over B of mu t minus nu t. And the other one as well. T in A slash B mu t minus nu t. That's by the definition of the measure. Okay, and what we have now obtained in this kind of situation is that we want to basically throw away something from this definition. So by definition, we have that for all t in A over B, so this expression here, we have that if you take the mu t, then this is less than mu t, because this is in the complement of the set B. So it doesn't matter what the point A is, but it's because it's outside the B, we have this. So in particular, mu t minus nu t, so this expression is always negative. So that's why, if we take this expression here, and I'll continue this from here, then what I can do is that I can just bound this from above by 0. So I can just take t in A intersection B mu t minus nu t as the thing that comes out. I just threw away that 0 away. It's actually strictly less than that if you want to be precise. And now you can open this again. So what you can see here is that this is now equal to mu A intersection B and then minus nu A intersection B. That's the kind of expression we obtain at this stage. Well, actually, we can just, we don't have to say that. We can just directly say that, okay, so basically at the same time, when you're in the B, we know that this is at least positive, because as mu t is at least nu t in when t is in B. So that's why you can basically bound this from above by just taking everything here. So you can just basically bound this by t in B in mu t minus nu t. So instead of summing just over the sets that are points that are in A intersection B, you just sum over all the B. So that's how you kind of got rid of the A dependence of the whole thing. And you can do this upper bound because you're not basically, there are not points that could just be subtracted down. That's because they are all non-negative inside the set B. And now we have this expression, we can just write this as mu B minus nu B, which is what we were claiming. And this, remember, this is now mu B minus nu B because the set is positive. This was what we said already earlier. So now we just have proven this expression. So we have proven that mu A minus nu B, nu A is at most this mu B minus nu B. Or we could just put it in like this, that we have the absolute value, if you want. And doing exactly the same as above with basically replacing B by B complement. So you basically, instead of like taking the intersection with B, you're taking the intersection with the B complement all the time, and then like replacing all the arguments with B complement. We obtain that if you take nu A minus mu A, so remember, notice that this is now at a different order. So this is mu A, this is mu A, and this is nu A, nu A. So if you take it at a different order, this is at most, I can put this as nu B complement minus mu B complement. So you had this order and that upper bound that you obtained in both cases. So now we can finally use the argument that we had above here. So we had this this in the first step, this kind of a mu b minus nu b is equal to nu b complement minus mu b complement. So you get actually the same value from different expressions. So this argument, this thing here, is just the same as mu b minus nu b, which is equal to the mu b minus nu b. So as in this case, so we had this mu b minus nu b as an upper bound. So in both cases, you have proven that there's the same upper bound for the distance between these two sets. So that implies, in particular, that the absolute value of mu a minus nu a, which is what we want to maximize, is at most this mu b minus nu b. So so this implies in particular that the total variation distance is at most mu b minus nu b. So this proves that part of the claim. I use this like a square notation with a dash to like say that we prove this particular claim. And okay, so we have now done the proof of this step 2, and now let me complete the theorem. So how would you then prove this thing? So basically, there's two steps that I maybe want to prove. So step 3 is basically then to prove that this mu b minus nu b is equal to the half of the sum of tzb of mu t minus nu t, absolute value of this. So that's like the next step that we want to check. So now if you use this like previous step, or actually we could just use the kind of basic example, but what we have here, like the first thing is to, let's start the proof of this. What we can do here is the first thing is that if you take this mu b minus nu b, then what you have here is, if you open this up, this definition here, you will see that this is equal to, so inside the expression, what you can put here is that this is equal to a half of the mu b minus nu b, and then plus nu b complement minus mu b complement. And why is this true? It's because if I take this expression, if you remember this, that this is equal to basically 2 times and then a half of this mu b minus nu b. I'm just like, I could subtract and subtract this out. I'm just putting the argument here that you can see why this is true. So first, when you open this up, you get that this is by the previous property. So this is these 2 times. So this is mu b minus nu b, and then plus mu b minus nu b, and then this was equal to nu b complement minus mu b complement by the step 1 that we already proved. So that's why you get this like an expression that we have with the absolute value in the outside. So this is very important because now computing these in both cases we get into something quite quite simple. Thus, if we compute this, we have that if you compute this difference, you get that this is equal to, first of all, t in ZP, where mu t is at least nu b nu t. This is the definition of b, so this is mu t minus mu t. So this is equal to, this is non-negative, we can see that this is equal to the sum of dzp, and mu t is at least nu t of mu t minus nu t. I'm doing this because in this way I'm able to like basically write down that this kind of difference becomes a summation over everything, but then you have to take a half at one point using this expression that you have here. That's how the half begins to come. So if I take now the nu complement, nu b complement, and then mu b complement, in the same way we have t in ZP, and now mu t is strictly less than mu t, that's the definition of the other one, and then we have mu t minus mu t. But remember that this is again, this is in this set, because nu t is bigger than that, this is again positive. So what I can do again, I can basically put the absolute value inside. So what I can obtain is that this is when t in ZP, when mu t is strictly less than mu t, and absolute value. So because this is positive, I can put the absolute value mu t minus mu t. And notice that this is the same, when it's inside the absolute value, this is the same quantity. So this is t in ZP, mu t minus mu t is mu t minus mu t, what we claim. So if we combine this, we obtain that mu b minus mu b plus mu b complement minus mu b complement is equal to the sum of these two. So what you get here is a sum over t such that mu t is at least nu t of the absolute value, the same quantity, and then you have the t such that the nu t is strictly less than mu t of the same thing, mu t minus nu t. So by combining these both together, we get actually the whole ZP of mu t minus nu t, which was the thing that we were looking for. So thus, if we combine this all together, we get that the distance of the mu b minus nu b, which was equal to this half of the, let's actually copy this, this was what we had here, inside here, and we get that this is equal to now half of the, because this is non-negative, remember that this is summing absolute values, this is we don't need to write the absolute values, we get this summation t in ZP mu t minus mu t, which proves the claim now. So we have now proven basically that this mu b minus nu b is equal to this half of the summation over these distances, but at the same time it maximizes the total variation distance. So we have proven that it's actually maximizes the total variation distance in the same way. So that's proof of the whole theorem. Okay, so that's all for today, and in the next lecture I'll plan to go a little bit into understanding about some maybe another identity that we have for this thing, like using the variational formula, for example, and then I'll go into the information theory and entropy, which is kind of the main topic of the other thing.